Good morning, good evening, good afternoon, everybody. My name is Alex Clemm, and together with my co-author, Toerless Eckert, I will present to you on high-precision latency forwarding over packet-programmable networks. The starting point for our work was the observation that there are many future networking applications which require support for high-precision service level objectives, actually much higher precision than is the case for most services today. And examples include, for instance, haptic communication and tactile internet, which require end-to-end round-trip latencies, which are extremely low for the closed control loops that these applications require. And similar stories for Industry 4.0 with remote industrial controllers, for holographic type communications, where users interact with holograms requiring rapid restart or rapid adaptation of media streams as viewing angles change, and so forth. Likewise, also for the case of resilient schemes, which require in many cases path performance transparency. So think, for instance, of a scenario where you duplicate or where you replicate packets, forward them over multiple path segments for resiliency reasons, only to recombine them at another point in the network. In that case, you would require near identical latency in order to minimize buffer space at the egress points to be able to deduplicate those packets. So what's the current state of the art in this area? Well, current state of the art are the best effort internet technologies, as well as various cross mechanisms. And in chronological order, a rough chronological order, we had in-serve, specifically in-serve guaranteed services, which used signaling, for instance, using RSVP to make bandwidth and buffer reservations across networking paths for committed and peak information rate throughput. And as a result, end-to-end latency could be controlled through per hop and per flow shapers, which would basically be allowed you to engineer paths for a given latency. Then there's diff-serve. This one introduced per class lighter weight traffic management based on prioritization, for instance, of different sources of traffic. Basically, this allows you to manage resources, bandwidth queuing buffers, and so forth, and allow you to determine which traffic should take priority over which other, but no hard latency guarantees are actually given here. Then we have IEEE 802.1 TSN. This is essentially an Ethernet layer 2 variation of in-serve guaranteed services with some enhancements for one-to-end path protection, where you have which allow for replication of packets across the disjoint paths, again for resiliency reasons. Then we have DetNet. DetNet does allow to put bounds on maximum end-to-end latency for again for certain paths. So a lot of effort in this area. However, a number of shared limitations between all of those. For one, basically, they all focus on mere optimizations of the end-to-end latency, and they generally do not support end-to-end latency, which is defined by an application and gives you specific quantified bounds. Likewise, the focus has been on maximum bounds, but no support for lower latency bounds, so that, for instance, in certain cases, you would not want to deliver packets soon. You would also want to deliver them no sooner than a certain time. And finally, the efforts are generally applicable not to variable bitrate traffic, only to CBR. So as a result, our problem statement was to provide a network service that will be inherently capable of supporting high precision SLOs. So specifically SLOs as they relate to end-to-end latency. And we wanted to support both in-time objectives, where a certain end-to-end latency would not be exceeded, as well as on-time objectives, which also allow you to specify, in addition to not to exceed, also a no sooner than boundary for this. We want it to be also applicable to any type of traffic, not just CBR. And we are focusing on end-to-end latency, not on other SLOs such as jitter or loss, and we don't consider them here. So just to visualize this, essentially our goal is for a service level objective, we specify a range. This is basically our SLO target, and we provide a lower bound, or user application provides a lower bound and an upper bound for the end-to-end latency which the packets must meet. And in the case, we have special cases when the lower bound equals 0. This is when we talk about an in-time guarantee, or when the lower bound equals to the upper bound, then we talk about on-time guarantees. So key to our solution was the observation that service levels can in many cases be decomposed, specifically end-to-end latency. And what this means is that basically the end-to-end latency between nodes A and D in this case is the same as the sum, or amounts to the sum of the latency between each of the segments that incurred. And this does mean that, for instance, if you incur a lower latency on one of the earlier segments, you can afford a longer latency in the other in the later segments, or vice versa. And of course, you can break down the latency a little bit further into the latency that is incurred by propagation, signal propagation across the link, as well as the various latencies within a node itself. And so this is what we leverage as follows. So our basic idea is that each node, when it receives a packet, makes a forwarding decision based on the latency expectation for that packet. So basic idea is, if the packet is early, make it slow. You can choose an action that puts it on a slow path, in a slow queue. You might buffer it when feasible, and so forth. On the other hand, when the packet is late, but still has a chance to just make it in time, you want to prioritize the packet. You want to speed it up. You want to make sure that you basically forward it onto the next hop as fast as possible. And finally, if a packet is so late that it is beyond recovery, so no matter what you do, it will arrive late, then in order to reduce congestion and improve service levels for other packets that otherwise might compete with it, you can also drop the packet early. And so this is executed on every node along the path, and this results in a distributed algorithm across the nodes on a path, which complements the on-node cross solution that we normally know. So benefits of this are, well, we meet our precision SLO targets. We do so even in the case when there is some non-determinism along the path, when there are some perturbations, if there are some link variation, link latency variations, because the idea is, well, for instance, what you lose in one segment, you can always make up in the next segment, and vice versa. Our concept is also easy to manage. There's no need to dimension and allocate, for instance, component SLO budgets in advance. We don't need to reserve resources a priori. And our concept is very elastic, which does mean it does allow it to recover, for instance, from slight jitters, path perturbations, and even poor decisions that were made by earlier nodes along the path. And then finally, and this is important for our community here at NOMS, is that this also inherently integrates a forwarding plane function of the data service with the ability to assess compliance with your SLO and assure the SLO. So basically, there are no separate mechanisms which are required to this. So we don't need PNPM, we don't need IPSLA, we don't need TWAMP, and so forth to assess this. All of this assessment and the measurements occur inherently as an integral part of the service. So when we look at the, so let's take a look at the behavior that occurs at each of the nodes. Essentially what happens is you receive a packet, you determine the SLO for that packet, and you assess the latency that was incurred so far. The way you determine that is actually you can carry these, you can carry the metadata for that as part of the packet itself. We'll see this in a moment, actually how that is done. And then with this information about SLO and the latency incurred so far, the node determines what is the latency budget. So basically, and for this, actually, there's another input that the node uses, namely the path prediction of what else is coming forward on the path. So for instance, how many hops are remaining along the path? What is the expected latency for the path going forward? This information can be known and communicated, for instance, through the control plane using IGP. It could be provisioned through a controller. It can be basically available through different means. Then using this input, So basically, how much more time does the node need to spend? How much time did it already spend? And what is the objective? Based on this, you get a latency budget with a minimum amount of time and the maximum amount of time that the packet can afford to spend within the node. You can have different heuristics to do that. Comparison of the different options and so forth is outside the scope of this paper, but we are looking at it for future work. Then with this budget, we execute the actual quas action, and this is the one that allows us to forward the packet within the allotted time delay that was put. And we look at this action in a little bit detail on the next slide. I wanted to also mention just that there is room for different quas schemes because you could try to optimize certain secondary properties beyond the SLO itself for the network. So in terms of the quas action, the algorithm that we chose consists of a cascade of 2 queues. The idea is that in the first stage, we try to address the lower bound of the packet, which basically means we slow down the packet up to the earliest point at which we can forward it. We do this by using a PIFO queue, in which we basically schedule a packet to the lower bound of the local budget that we determined. Then, once the packet is ready for transmission, we then put it into a second queue, the FIFO queue, which essentially is supposed to address the upper bound of our boundary. And this basically, well, the question is what happens if you have multiple packets which are ready for transmission at the same time. You need to determine which one goes first. So basically your classic quas mechanisms. And again, this conflict resolution occurs here. And in our case, we are simply choosing the packet which has the least remaining local budget. This one is sent first. So here's a brief example of how the thing works. So you see a path here with the link latencies. Service level objective is for on-time service guarantee with 8 milliseconds. What happens is the packet arrives at the first node. It finds out, okay, the local budget is, well, 8 milliseconds is the SLO. You need to subtract from it the 1 millisecond, which was already spent, and the 1.5 milliseconds, which is the remaining end-to-end latency for the remainder of the path. So this gives you 5.5 milliseconds divided by the number of remaining hops, which is 3, and basically you have a budget of 1.83 milliseconds that you can locally spend. So let's assume in this case, basically the actual latency that is spent is 1.5, so actually a little bit less. And then what happens at the next node, basically you do the same thing. It does again the same assessment. In this case, it comes to the conclusion, well, it can spend a little bit more time because it was sent earlier, the packet. So you see actually now the elasticity here at work. It's a 2 millisecond. And in this case, basically it forwards it a little bit later. And the game repeats. And finally, actually, you have an on-time delivery of the packet. So in order to realize this, we needed to also a protocol for our packets. We needed a protocol to carry the SLO parameters as well as the latency measurement metadata. And instead of designing a custom protocol, we decided to use a packet-programmable networking framework called NewIP with a protocol called BBP. Essentially, this does allow us to carry the parameters as metadata as well as the latency forwarding semantics as part of a command that gets simply invoked as part of the packet. We don't have time to go into the background here, just very briefly. Essentially, traditional packets get complemented with a contract collateral, which includes the commands to specify semantics for the packet, as well as metadata, which gets inserted between the header and the payload. An example of the packet can be seen here. So you would have here this LBFify action with the SLO parameters, as well as the packet latency that was incurred so far, which is essentially updated at every hop. And then the whole thing maps to a BBP contract, and you see this here. It's basically it's a 16-octet payload tax that you need to pay essentially, but the whole thing fits into 16 octets in the packet. We did build a POC for this. Actually, it's available open source on GitHub at the URL that you see here. What the POC uses is, well, it provides a network emulation. Um, uh, Forwarders are mapped to separate cores on a Linux server. We're using UDP ports as link layer interfaces, which are used to basically pass UIP BPP packets. And after test runs, we are logging the packets and analyzing their timings and so forth. We also had a demo here, which we showed yesterday, in case if you're interested to see the system in this is the test topology that we used. So between a sender and a receiver, we have 4 forwarding hops. And at each of those forwarding hops, we can introduce competing traffic, which basically allows us to perturb or compete with our high precision traffic between the sender and the receiver there. This brings us to our assessment. So to do our assessment, well, we started with creating a baseline, simply the baseline of best effort traffic with no particular SLO. What you see here depicted is always the minimum, the average, and the maximum end-to-end latency incurred by the packets for the flow. The number in square brackets that you see is the difference between the max and the min. That you have. And the interesting thing that you can see here is that as you introduce competing flows with the best effort flow, well, any time that you lose earlier, you can never make up later. So basically any perturbation introduced only keeps growing basically with the length of the path and with the number of perturbations. So now, basically, the next run shows now we run the same thing again, exactly same setup, but with an SLO lower bound of 700 microseconds. And in this case, we can see the effect nicely here. First of all, when there's no competing traffic, you can see every node basically increases a little bit of time, is evenly divided up due to this budgeting algorithm. But an interesting effect comes into play when you look at the competing flows. Because now if there's a perturbation introduced early on along the path, actually the time that was lost, so to speak, is for the latest packets is being made up across the path here. So you can see that actually by the time the packet reaches the receiver, you don't even know that the traffic was ever perturbed. And this is true even when you have more competing flows, but of course if you have less nodes remaining to make up that the difference, of course then you can basically reduce this difference a little bit less. But in each case you're always meeting the SLO. So basically this is what you always see basically at the receiver. It never receives a packet before 700 microseconds. Then finally, we wanted to take a look at the effect that the SLO boundaries themselves would have. So in this case, we have a lot of, now basically we have the same type of competing flows in each of the runs, but we introduced growing lower boundaries of the SLO from 700 to 1100 microseconds. And what that does is here that it gives, well, the less ambitious your SLO gets, the more slack individual nodes get, the more budget individual nodes get to play with, and actually which allows them to make up for any variations that are occurred earlier in the path, even more so than in the beginning. So you see this effect here very pronounced, where in the end, even for perturbations which are introduced very late, pretty much all the packets will arrive with very little delay variation. So in conclusion, latency-based forwarding is a new approach to achieve high precision end-to-end latency SLOs. There are a number of interesting properties about this. For one, it allows us to deliver this in time, or deliver in time and on-time services regardless of the bitrate variation. So we don't need to have a CBR that is known in advance or so. Also, it's a distributed algorithm. It works in conjunction with and complementing on-node cross solutions. And its elastic property makes resulting services very resilient against any perturbations in network fluctuations in traffic load and so forth. In terms of the cross actions and in terms of the heuristics to determine the local node budget, multiple variations are possible. We will basically look at as part of that as future work. And we wanted to also mention that this provides a very nice showcase or use case for the applicability of the new IP BPP framework to use case of high precision networking beyond the uses, for instance, for smart telemetry and so forth, which have been demonstrated in the past. And this concludes our presentation. If you have questions, comments, or suggestions, we'd love to hear from you. Yeah, thank you and have a nice day. Bye.